So previously, we talked about this spectral decomposition of this inner product. Right? Our goal was to get at this shifted convolution right here, where here AM is this Fourier coefficient of a holomorphic weight K Cuss form. And spectral decomposition gave us this in terms of some inner product or some sum of inner products. And what we got, well, it was kind of a mess, but conceptually, this is pretty good, because if you look at where it's coming from, all of these pieces individually can be understood conceptually a little bit better than the shifted Dirichlet series, where we really have no idea what's going on. And from a more practical perspective, even though this thing is quite messy, there's nothing in it that is as daunting as this shifted convolution that we just don't understand at all. This is just some gamma functions. It's this convolution, but this is not a shifted convolution, so it's not so bad. You've got these L functions, etc., but it's all stuff that in principle you can understand. And the second term is similar, and again, also in principle stuff that you can work with if with just a little bit of grit. So this lecture is going to be about taking the spectral decomposition that we found and looking at it and seeing what we can glean from it. So the first question, and the question I'd be most interested in, is the following. What is the growth of, and now here I'm just going to do the sum n less than x of an conjugate times sigma 2w minus 1 of n plus L. So you see this this shifted convolution is just the Dirichlet coefficients here. And you can, if you want, include this normalization. If you just omit the s here, this is a very natural normalization for this quantity, because am is going to be about m to the k minus 1 over 2. And the sum of divisors function, the natural normalization is m to the w minus 1/2 in light of the functional equation. So this is going to be the question that I think first occurs to people. And we can ask, can we say that it's something like constant times x to the alpha plus big O of x to the beta? Stuff like what we've done previously when working with Peglon's formula. And what we know from that is that the answer depends on the poles. And I mean, here I'll write the right-hand side. Of course, the right-hand side and the left-hand side are equal. So, so the poles of the right-hand side and the poles of the left-hand side are the same, but I write the poles of the right-hand side to emphasize that here we really don't know what the poles are going to be. I mean, I guess we know the gamma function in this denominator, when we multiply it out, we know where that's going to have poles. But otherwise, we don't know anything about this. But here we can just look at this and figure out where the poles are going to be. So let's see what we've got. So in this term, remember, we're looking just at the s dependence, because we're going to look at this integral along the line sigma sufficiently large of our Dirichlet series am sigma 2w minus 1 m plus L conjugate here over m to the m plus L to the S plus K minus 1 over 2 plus W minus 1/2, and then we have an X to the S ds over S here as before, and this is sum m from 1 to infinity, and right, just taking this as this thing, multiplying through by this, let's look at the poles. We're looking at poles in S, so what S dependence do we have? Well, if we think about it from coming from here, these two terms, these have no S dependence. The only S dependence is going to come from this Poincaré series, P sub L. So, right, this is P sub L Z S bar. And similarly, this has no S dependence. It's kind of weird to include this because this is, you can think of this as a constant, right? You could have picked an orthonormal basis of Moss forms. But anyway, the point is that the only S dependence is going to come from this inner product of the Moss form with the Poincaré series and this inner product of the Eisenstein series and the Poincaré series. So let's go through our big mess and see where those appear. Well, we've got the S dependence appearing here, and here we see that we have poles with the real part of S is 1/2, assuming that these RJs are real. And this assumption, this is Selberg's eigenvalue conjecture. So it's not known, but anyway, this will give you some bound this will tell you what your growth is going to look like. The gamma function has no zeros, so we don't need to worry about this denominator, and there are no other s's here. And then it's the same thing here. The only S dependence we have appears with poles appears in this term, right? We've got an S dependence in some other places, but these things don't have poles. So here, again, remember we're integrating along the line real part of lambda is 1/2. So this is a pole when the real part of S is 1/2, because the rightmost pole of the gamma function occurs when the argument is 0. So that means that S minus 1/2 is going to have the same real part as lambda minus 1/2, and the real part of lambda minus 1/2 is 0. So this is the rightmost pole. And we did have this one denominator here that we need to think about what happens when we multiply through. So what happens here, this is going to have a rightmost pole when the real part of S is minus 1/2 minus k minus 1 over 2. So this is strictly less than 0, right? Because we're assuming that this is going to be a holomorphic cusp form. So this weight is going to be, right, I'm going to assume that this weight is a positive even integer. So this is not going to be as close to the right as these poles. So we could guess reasonably that the sum m less than x, when we think about shifting this contour, the first poles we're going to pick up are when the real part of S is 1/2. So we can guess that sum am sigma 2w minus 1 m plus L over, and so here we're going to have this this normalization as follows when we use Perron's formula, because this is really what the Dirichlet coefficient is. And we would guess, based on the fact that the rightmost poles are at s equals 1/2, that this is going to be less than x to the 1/2 plus epsilon. But this is just a guess. And why is it just a guess? Well, because to prove this, we need to do some analysis on the size of the residues that we're going to get these poles, because we have, in this term, infinitely many poles with real part 1/2, assuming this Selberg eigenvalue conjecture, right? We get some for every, we get this pair of poles for every Moss form, and there are infinitely many Moss forms, and we get more and more as the eigenvalues get bigger. That's something that we can talk about otherwise. And we also don't know how big these coefficients are, et cetera, et cetera. So we don't know, we can't say for sure that this is going to be a growth of x to the 1/2 for this sum. And similarly here, we haven't really looked at how big this coefficient is. Maybe integrating over it makes it blow up. Maybe it doesn't even converge. So I'll have to be careful. But just looking at it, a reasonable guess would be that this is the growth. It turns out that this is beyond the reach of current techniques. But it is a reasonable guess. We'll see what we can prove in a later lecture when we start looking at the size of each of these individual terms. But it's probably going to be something like x to the 2/3 if I had to guess right now. I'm not sure what we'll get, but I would guess that it's x to the 2/3 is the best we can do with current techniques. But certainly what we can do, and what we won't do for a little bit, but what is provable is the sum, which I'll just copy paste here. That this sum, you can prove that this is less than x to the beta, let me say x to the delta, for some delta strictly less than 1. So you can get a power savings, right? Because you have x terms. The terms are, sorry, it shouldn't be, it should be 1 plus w minus 1/2, right? Because the size of the sum of divisors function is going to be m to the 2w minus 1, and we're dividing by m to the w minus 1/2, so we should still get that this ratio is, each term the ratio should be of about size m to the w minus 1/2, and you have about x of them, so you would expect that if there's no cancellation, they'd all be, you'd get a sum this big, so you can get power savings in this way, and maybe with some assumptions on w. But anyway, you can get power savings is the point, and but you can't really get a constant term or a coefficient here. You can't know exactly what the asymptotic growth is. It's going to be a sum of poles, all with the same real part, and it's gonna oscillate. You can say what the behavior is exactly because this is an equality, but you can't get a satisfying answer like we had previously. In fact, I mean, it's just not going to be true that the growth is something that looks like this, right? It's going to oscillate in other ways. So ultimately, the spectral decomposition that we got, it kind of told us, I mean, it tells us everything about our shifted convolution in the sense that if we multiply stuff out, we do really get an identity with stuff that we understand on the right-hand side. But in terms of writing down something nice, it's not so great, but we can prove cancellation, which is important in a lot of contexts.